Welcome back to Electronics Explained Simply. Before we get into this episode, we're going to start with a short quiz based on the previous video. Take a moment to think through each question, and let's see how you do. All right, let's begin. Question 1. What is electrical resistance? Question 2. What is the unit of resistance? Question 3. Which formula correctly represents Ohm's law? Question 4. Which material is typically a good electrical conductor? Question 5. What happens to the resistance of a wire if its length is doubled? Question 6. What happens to resistance if the cross-sectional area of a wire is doubled? Question 7. What does resistivity describe? Question 8. Why does resistance in most metals increase with temperature? Question 9. Why does a thinner wire have higher resistance than a thicker wire of the same material and length? Question 10. Which statement about conductivity and resistivity is correct? All right, great job getting through the quiz. In this episode, we're going to build on everything you already know about voltage, current, and power, and start looking at how real materials and real-world design choices affect how circuits behave. We'll talk about why some materials conduct electricity, why others don't, how heat is generated and transferred, how wire size matters, and finally, how grounding actually works in practice, not just in schematics. This episode ties together physics, electronics, and practical design. So take your time and pause when needed. Electrical resistivity of materials. Not all materials conduct electricity the same way. One of the key properties that determines this is electrical resistivity. Good conductors like copper or aluminum have very low resistivity, meaning electrons can move easily. Insulators like glass or plastic have extremely high resistivity, making electron flow very difficult. Semiconductors sit in the middle. Their resistivity can change dramatically with temperature, impurities, or applied voltage, which is exactly what makes them so useful in electronics. To really understand why materials behave differently, we need to zoom in to the atomic level. Electrons don't have arbitrary energy values. Instead, their energy is quantized, meaning electrons can only exist at specific energy levels. Think of these levels like steps on a ladder rather than a smooth ramp. Importantly, just because an energy level exists doesn't mean it's occupied. Electrons always try to fill the lowest available energy states first. Energy bands in solids. When atoms come together to form a solid, individual energy levels merge into what we call energy bands. The two most important bands are the valence band, where electrons are normally bound to atoms, and the conduction band, where electrons are free to move through the material. Between these bands is the energy gap, sometimes called the band gap. This gap plays a huge role in determining whether a material acts as a conductor, insulator, or semiconductor. Conductors versus insulators versus semiconductors. In conductors, the valence band and conduction band either overlap or are extremely close together. That means electrons can move freely, even with a very small applied voltage. Insulators, on the other hand, have a large energy gap. Electrons simply don't have enough energy to jump into the conduction band. Semiconductors sit right in between. Their energy gap is small enough that heat or voltage can push electrons into the conduction band, allowing controlled conduction. Temperature effects on resistance. Temperature affects materials in very different ways. In metals, higher temperature causes atoms to vibrate more, increasing collisions with electrons, which raises resistance. In semiconductors, higher temperature actually creates more charge carriers, lowering resistance. This opposite behavior is why semiconductors are so sensitive to heat, and why thermal design is critical in electronics. Heat and power in circuits. Whenever current flows through a real circuit, power is being used. That power doesn't disappear. It gets converted into other forms of energy. Sometimes that's useful work, like light from an LED or motion from a motor. But very often, power ends up as heat, and excessive heat is one of the biggest enemies of electronic components. Ohmic heating, also called joule heating. When power is converted into heat due to resistance, it's called ohmic, or joule heating. The key takeaway is that heating increases with the square of the current. Doubling the current doesn't double the heat. It increases it by 4 times. This is why high current circuits require careful design, thicker wires, and proper cooling. Thermal heat conduction. Heat always flows from regions of higher temperature to lower temperature. How fast that happens depends on the material's thermal conductivity and the shape and size of the object. Metals transfer heat very efficiently, while materials like air and plastic are poor thermal conductors. Thermal resistance. Thermal resistance works very much like electrical resistance. It tells us how much temperature rise we get per watt of heat flow. A long, thin path resists heat flow more than a short, wide one, exactly like current in a wire. This analogy makes thermal analysis much easier once you're comfortable with Ohm's law. Importance of heat management. Excessive heat doesn't just damage components, it changes how they behave. Resistance values drift, semiconductors become unstable, and long-term reliability drops sharply. That's why heat sinks, airflow, and proper power ratings are essential in real designs. Wire gauges, AWG system. Wire size is defined using the American wire gauge, or AWG system. Counterintuitively, a smaller gauge number means a thicker wire. Thicker wires have lower resistance and can safely carry more current. Using wire that's too thin can cause excessive heating, voltage drop, or even fire hazards. Choosing the right wire gauge. When selecting a wire gauge, you always want to consider the maximum current, the length of the wire, and a reasonable safety margin. Even if a wire technically works, choosing a thicker gauge improves efficiency and reliability. What is ground? Ground is one of the most misunderstood concepts in electronics. In many circuits, ground is simply a reference point, often defined as 0 volts. It doesn't always mean a physical connection to the earth. What matters is that all voltage measurements are relative to this reference. Earth ground versus circuit ground. Earth ground provides safety, especially in mains-powered equipment. Circuit ground provides a stable reference for voltages and signals. Sometimes these are connected together, but not always. And connecting them incorrectly can cause serious problems. Ground loops and noise. When multiple ground paths exist, ground loops can form. These loops allow unwanted currents to flow, creating noise, voltage errors, and instability. This is especially problematic in sensitive analog and mixed signal circuits. Single-point grounding. A common solution is single-point grounding, where all grounds meet at one location. This minimizes voltage differences and reduces noise coupling between parts of the circuit. While not always practical, it's a powerful concept to understand. Analog versus digital grounds. Digital circuits create sharp current spikes, while analog circuits are often very sensitive to noise. Keeping analog and digital grounds separate and joining them at a single point helps prevent digital noise from corrupting analog signals. Common grounding mistakes. One of the most common beginner mistakes is assuming that any ground symbol means the same thing everywhere. In reality, the symbol can represent very different physical connections. Understanding what type of ground you're dealing with is critical for both safety and performance. In this episode, we saw how materials, heat, wire size, and grounding all interact in real electronic systems. These concepts go far beyond equations. They determine whether a circuit is reliable, safe, and accurate. As we continue, you'll see these ideas come up again and again in practical designs. Everything you've seen in this episode is based on Practical Electronics for Inventors, 4th edition. It's an excellent book for building a strong foundation in electronics, and we'll continue using it as a reference throughout this series. If you found this video helpful, make sure to subscribe so you don't miss the next episodes. Coming up, we'll keep building on these fundamentals and gradually connect theory to real-world electronics and PCB design. If you have questions or topics you'd like me to cover next, leave a comment below. Thanks for watching, and I'll see you in the next video.